Hi everybody, I'm Roger Noble and I would have been leading the Astronomy Week at Bradwell this year. However, because of the COVID-19 pandemic, we can't do that face to face as usual, and so instead I'm recording some of the talks that I would have given. There've had to be some changes, unfortunately, but I hope that you still both enjoy and find them interesting. I'll also apologise in advance for any extraneous noises on the recording. I'm starting with the introductory lecture, which I've called Our Place in Space, and it sets the scene, so as to speak. By the end of it, I hope that you do indeed have a good feel for how we are a part of the universe. So, here we go. The first talk. So, here goes. Now, some of you may recall a quotation from Douglas Adams' radio series and books, The Hitchhiker's Guide to the Galaxy, and it goes something like, "Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts to space." Well, space is big, mind-bogglingly big, but as I said, by the end of this talk I hope you'll have a good idea of our place in it. On a clear night, have any of you noticed condensation forming on the roofs of cars? You know, in winter it may freeze. Now, why is that? Car roofs normally face upwards, facing the universe in general, and in fact most of the Earth's atmosphere, which holds the heat at night, lies within about 10 miles of the surface, although in fairness it does stretch out as far as 300 miles. And the universe as a whole has a temperature of about minus 270 degrees centigrade or thereabouts, and it's that your car roofs are facing, so it's not that surprising that they get cold. So the ice on your car roofs tells us that space is cold, and incidentally not that far away. It's cold, but it's not empty. We can see other stuff out there. The Earth is not alone, which leads us obviously to the next question: what other stuff? What is our place in space? Well, let's start with something close. The moon. Most people know the moon. You've seen it up in the sky, quite close. How close? I can't do a demonstration for you, but here's something you can do at home. Take a party balloon, sort of roundish, blow it up as far as it will go, and it'll probably be about 25 centimetres or so across. And now a tennis ball. Hold those two next to each other, and that's roughly the right scale for the Earth and the Moon. How far apart do you have to put those in order to get the correct scale for the Earth-Moon system? Well, start walking, because they actually need to be about 8 metres apart. The Moon is 250,000 miles from us. That's about 400,000 kilometres, but that's close for astronomers. Beyond the Moon things get further apart, so I'm going to have to change scale. And again, here's something you can do at home. Go and find a loo roll if you've got any left after the pandemic panic buying. And I'm going to represent the distance from the Earth to our local star, the Sun, by one sheet of toilet paper. And then we can mark off on that, on the roll, the other planets that we have in our solar system. And Mercury is about halfway along one sheet from the Sun. Venus is about 3/4 of the way. And the Earth, as I said, we've represented by one sheet. Mars is a sheet and a half. After that there's a bit of a gap, and Jupiter, the next planet out, is actually about 5 1/4 sheets away. Saturn, 9 1/2, Uranus, a little over 19, and Neptune, the furthest planet, about 30 sheets. Beyond Neptune, things get even further apart. Now, I just went and checked our toilet paper, and in fact there are 240 sheets of paper on average in a roll these days. So on that scale we would actually need somewhere in the region of 1,130 rolls of toilet paper to let me mark the position of the nearest star, Proxima Centauri. And Proxima Centauri is shown here on this picture on the right. You see this little red circle? I'm sort of pointing the cursor around it at the moment. That is the star Proxima Centauri, and apart from the Sun, that's the closest star to us. 4 years ago, in August 2016, the European Southern Observatory actually announced the discovery of a planet about 1.5 times the mass of the Earth orbiting that star, and it goes around it once every 11 days. But that's a very faint star. The planet is very close to it, and that's actually in the so-called habitable zone. That is, it has a surface temperature suitable for liquid water to exist. Now, it might surprise you to learn that astronomers don't usually regularly use toilet paper as a means of expressing the distances. We need some other measure, and I'm going to introduce that now so you know what I'm talking about in later slides. Now, when I turn on a torch, I don't normally expect to have to wait until its light reaches whatever I'm pointing it at. But actually light does have a travel time. It travels at a finite speed. And I'm going to show you a short video clip of light travelling from the Sun past all of the planets in our solar system towards the dwarf planet Pluto. And I'll start that now. Now, here's a little beam of light. See where my cursor is, here at the left next to the Sun. And this is in real time now. So you can watch it moving slowly outwards, very slowly outwards. Even light at 300,000 kilometers per second, the distances are so huge, it takes a long time. So all of the planets here, the distances from the Sun are to scale, and their sizes are to scale as well, but exaggerated by a factor of 1,000, so you can see them. Now actually I said this was a short video clip, and it's short because I'm going to cut it short. I'm not going to show all of it to you because it lasts for nearly 5.5 hours. Although it's probably good if you want a relaxation. In fact, I'm not even going to wait for the light beam to reach the Earth. And you notice here, it hasn't actually quite reached Mercury yet. And in fact, it will take 8 minutes, just over 8 minutes, to reach the Earth from the Sun. And for more distant objects, it'll take much, much longer. And you can see it marked out here that for Pluto, the dwarf planet Pluto, it will actually take about 5.5 hours to reach. And so we can say that the Earth is 8 light minutes from the Sun, or that Pluto is 5.5 light hours from the Sun. And for very distant objects like that closest star, Proxima Centauri, that is actually about 4.25 light years away. It takes light 4.25 years to get between us and that star. So here's a comforting thought for you. If the sun ever went out, we wouldn't know about it for 8 whole minutes. Now, don't lose sleep about this though. It isn't going to happen, and it isn't going to happen for billions of years. So let's cut that now. I mentioned the sun. The sun is a fairly small to middle-sized star, and here's a couple of pictures of it taken in normal visible light in 2 different years. And the one at the top right, if I can find where I put the cursor here, was taken in 2001, and the one on the bottom left down here was taken in 2006. Now obviously there's a difference. The one on the top right is spotty, and the surface of the sun we call the photosphere, and so the photosphere has lots of spots on it, whereas in 2006 there were none. And the sun actually has an 11-year cycle of activity, and the more sunspots on it, the more active is the sun. And in fact, for the last year or two, the sun has been going through really quite a quiet patch, although it might just be starting to pick up now in sort of 3/4 of the way through 2020. Let's take a closer look at the sunspot. Here's a good close-up view. It's rather a nice picture, this. I really like it. So here's some sunspots. They are vast in scales. These are probably larger than the Earth, and they are the locations of very strong magnetic fields. And the magnetic fields actually suppress the normal convection currents coming from the sun. Look around the sunspots and you see all these little lumpy bits. It's called granulation, and these are the tops of convection cells. So if you boil water in a kettle or in a pan, you'll get bubbles coming up to the surface. You can see them bubbling out on the top, and this is kind of like that on the sun. But the strong magnetic fields suppress those, and so you end up with these dark spots where the magnetic field sort of bursts out from the edge of the sun. And this bit here, the black bit, is a few hundred degrees cooler than the brighter yellow bits on the photosphere. And we can see the effects of these magnetic fields because they bend some of the gas coming around the sun. And I'm going to show you another movie now, another short clip, to show this happening. This is speeded up, and you can see the sun turning, and over here, really rather nice, the gas from the sun being forced to follow these magnetic field lines. Now, these big magnetic fields are the source of solar flares, and a flare can inject considerable quantities of material out into space, which, if it's directed towards the Earth, can cause aurorae. That's the northern and southern lights. It can also threaten astronauts, disrupt satellites, and even hold power grids. And here's a video of a fairly large flare that happened in June 2011. So just watch down here at the bottom right. And there it goes. Now remember I said that light takes 8 minutes to reach the Earth from the sun. The high energy particles that are emitted by these flares can often make it that distance in a couple of hours, although it can be as fast as 15 minutes, so they're travelling at really quite a speed. And the material that's thrown out of the sun on things like this is called a coronal mass ejection, so that's real material and would normally take a few days to reach the Earth. And in fact there are 2 spacecraft at the moment flying quite close to the sun, or can get quite close to the sun. There's NASA's Parker Solar Probe, and ultimately its orbit will take it to within 6 million kilometres of the sun. and there's the European Space Agency's Solar Orbiter, which doesn't go as close as the Parker Solar Probe, but it's at a high inclination orbit, which means it will be able to study the Sun's poles, which up until now has really been quite hard. We don't really see these very well at all. Anyway, what we'll continue doing now is, starting at the Sun, we'll travel out at the speed of light, leaving the Sun, and go out throughout the solar system. So here's a sort of schematic of the solar system. Again, the size of the planets aren't to scale. So we've got the Sun here, we've got Mercury and Venus, and here's the Earth. And so here to here, the speed of light takes us 8 minutes. So that's 93 million miles, or about 150 million kilometres. And I'm going to skip Venus and Mercury, and I'm just going to show a short video clip of the Earth, because it's nice. And this, we've got the Moon going past. Here's the Moon going in orbit around the Earth. And this was actually taken from a satellite about 1 million miles out from the Earth. The Earth is actually unusual, at least in the solar system, for having so large a moon in proportion to the size of the planet itself. So we'll keep on going, and we reach the next planet out, Mars, and again, travelling at the speed of light, we'll get there in about 12 minutes from the Sun. It takes a typical spacecraft about 6 months or so to make this. And here's a spacecraft's view of Mars. A few things to note about it, especially up here at the top there's the polar cap, North Polar Cap, South Polar Cap's hidden, and then there's clouds. And these are actually called orographic clouds, and a bit like on the Earth, orographic clouds form when air is forced upwards by a large mountain mass, say, and it cools and the water vapour condenses out. And there's a good example of that happening here on Olympus Mons on Mars, and that's actually by far the largest volcano in the solar system. It's 22 kilometres high and is about the size of France. Okay, the other thing to notice on this is this large canyon system down here, which is 600 kilometres across at its widest. It's 3,000 kilometres long, so all in all it's about 4 times the size of the Grand Canyon on Earth. And there's currently one remotely controlled rover still active on Mars, Curiosity, which landed in Gale Crater in 2012, and it took the following image in September 2015. Now, think about this picture for a bit. It looks like the sort of light that you get on Earth. The sky is blue, for example, and that's strictly speaking not the case on Mars. On Mars, the sky is actually reddish, and part of the reason for changing the colour balance of the picture here, because it makes it a lot easier for geologists to spot different types of rock if they're being viewed under the same sort of conditions that you would get on Earth. Okay. Now, the Curiosity rover has been on Mars for 8 years now, as of August this year, and last year it took a panoramic view, and NASA have made a little video of this, which I'll turn on.
This is the largest and highest resolution panorama the Curiosity rover has ever taken. It's made up of almost 1,200 individual images taken over 4 days. The rover's body is too close for the Mastcam's telephoto lens. but we were able to capture the rover using the other Mastcam lens. The higher resolution version is nearly 1.8 billion pixels. What I love about this panorama is that we can zoom way in and see details far in the distance. When you start to do that, you can see the rim of the crater we're inside of all the way to the north. Here's an impressive sight. 20 miles away is Slangpost Crater, just inside Gale Crater's rim. End to end, Slangpost is 3 miles wide. Something huge must have struck here. Whenever I start to think that Mars looks familiar, sites like this dramatic impact crater remind me that we're looking at a different planet. Curiosity is exploring a clay-bearing region on the side of a mountain. This ancient landscape was the site of lakes and streams billions of years ago. They left their clues in the finely layered, clay-rich rock. This crumbling cliff is the edge of the green hue pediment. It's a vast sheet of rock draped over the side of a mountain. It must have formed after the lakes disappeared and the mountain took its present shape. Did it once extend even farther out? Curiosity looks a bit like an abstract painting here. That's because this is a 360-degree perspective. The image is warped, like looking through a fisheye lens. You can make out some amazing details on the rover itself. This is the shadow of Curiosity's mast. Here's RAD, an instrument that detects radiation from the sun and space. Thanks to RAD, we have a better idea of how to protect future astronauts on Mars. Why are there severed tubes and wires on the rover? These tubes were part of the fluid cooling system that circulated throughout the spacecraft that flew the rover to Mars. These wires were like an umbilical cord for data. They were cut during landing. In spite of all the dust, our sundial still tells us to explore. Trailing behind the rover, you can see our tracks, including where we climbed up a hill. Even after 7 years on Mars, Curiosity is not done making tracks yet. Panoramas like this are like a window to another world. Explore it yourself in a 360 video. Look for the link in the description.
Now I'm recording this in late June 2020, and in July next month, from when I'm speaking, NASA hopes to launch the latest rover to Mars, and this will be called Perseverance, and that should arrive in Jezero Crater in February 2021. It will be similar in size to Curiosity, but it will carry a small helicopter, which should make for interesting pictures. Again, at the time that you're hopefully seeing this talk, Mars will rise at about 10 p.m. in the evening. So let's continue onwards and outwards. This is where we were. We're on Mars, around here. Beyond Mars, there are the bulk of what are called the asteroids, lumps of rock, basically, mostly uneven in shape. The largest, which is actually big enough to be round, is Ceres at 933 kilometres, currently with a spacecraft in orbit around it, the Dawn mission, although the mission ended in 2018, it's run out of fuel now. And a couple of asteroids have been in the news recently. The Japanese spacecraft Hayabusa 2 has collected samples from the near-Earth asteroid Ryugu, and that will return them to Earth in December 2020. And the NASA mission, OSIRIS-REx, has travelled to another near-Earth asteroid. That's an asteroid which actually has an orbit which takes it close to the Earth. And that arrived in December 2018 at the asteroid called Bennu. and again the intention is to collect samples from the surface. Now this has actually been rather complicated, or will be rather complicated, because it turns out that Bennu is an extremely rugged surface, and 4 potential sample collection sites were identified, and this little movie just shows those. So here's Bennu. So 4 sites labelled Osprey, Kingfisher, Nightingale and Sandpiper. And in fact the first attempt will be made in October this year, 2020, from the Nightingale site, and if that is successful the mission controllers will be extremely grateful, and the spacecraft will then leave Bennu and return the sample to Earth on, hopefully by the 24th of September 2023. The spacecraft will leave Bennu, so sort of middle of next year. Okay, let's keep going out. So here's where we were. We got the asteroids. So I'm going to zoom out now, and I want you to keep an eye on this belt of asteroids here as we zoom out. So here we go. Right, the belt of asteroids is now here, right down in the middle. So we've changed scale by quite a bit. And the first planet we come to beyond the asteroids is Jupiter, the largest planet in the solar system, the first of the so-called gas giants. And at the speed of light, 43 minutes out from the Sun. And again in August, when hopefully you're listening to this, Jupiter will be visible towards the southeast by the time it's dark. And this is about 11 times the size of the Earth, and if you tot up all the other planets in the solar system, Jupiter is still 2.5 times more massive than all of the rest of them put together. So it really is big. It dominates the solar system, apart from the Sun. And what you're looking at here is the tops of really clouds. Jupiter is largely atmosphere. There's probably something solid or solidish towards the middle, but what we're seeing is gas, atmosphere itself. And it has these huge storms going in it. Here's one, a great red spot, which has been going for at least 300 years. And Jupiter currently has a spacecraft in orbit around it called Juno, and that's returned some really spectacular images. And because Juno passes over Jupiter's poles, it's enabled us to see various bits which we really haven't been able to see before. Here's one. This is Jupiter's south pole, and it was quite a surprise because the degree of turbulence in the atmosphere here was quite unexpected. Saturn's, for example, is really quite regular, and these little oval features here are cyclones, and they're about 1,000 kilometres in diameter. And we've got some other really beautiful images from Juno. Here's one of the clouds, and one of that great red spot that I mentioned, this sort of storm that's been running for hundreds of years. Okay, so Jupiter, I said we reach after 43 minutes. Let's keep going out. Saturn will reach after 79 minutes. Uranus over here, 160 minutes. Neptune, a bit over 4 hours. And then we hit the Edgeworth Kuiper belt of smaller rocky bodies, and we'll have passed that by about 7 hours. But my next stop off though has got to be Saturn. Saturn is really beautiful, fantastic planet. It's about 9.5 times the size of the Earth, goes round the Sun in about 29.5 years, and its rotational period, its days, about 10 hours, 10 and a quarter hours. An interesting fact about Saturn, together with some of the other gas giant planets, is that they might just rain diamonds. Carbon in Saturn's atmosphere actually rains down, gradually being compressed as it goes deeper and deeper into the planet, where the pressures are enormous, and possibly then gets compressed into diamonds up to about 1 centimetre across. Unfortunately, they carry on going down, and by the time they go about 35,000 kilometres down, the temperature and pressure become so extreme that they simply don't survive. Saturn has the most prominent rings in the solar system around it. In fact, some of the other large planets have much fainter and smaller ones, but nowhere near the sort of detail and size and wonder that you get on Saturn. Have a look at some of the detail here. Notice the complex banding. And most of this structure, this fine structure, is because of gravitational interactions with Saturn's moons. And Saturn has over 60 moons. And the Cassini spacecraft, which took these images, was actually deliberately destroyed in Saturn's atmosphere after doing a series of orbits which took it through the gap between the planet and the rings. There's a sort of 1,500 kilometre gap. And Cassini had been at Saturn for many years, but it was running out of fuel. And the Jet Propulsion Laboratory and NASA, who were running the mission, didn't want it to accidentally land on one of the moons, because some of those moons might just have some sort of life on them, and they didn't want to land an Earth-based thing on those just yet. So I'm going to show you a short video about the end of the Cassini mission. It's a bit melodramatic, but it is quite fun.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a 1 million-mile trek to Saturn. We have cleared the tower. Its program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
To the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
That's one quite emotional, really. The rings are actually very thin. Generally, they're probably not more than about 10 metres thick, although probably up to 1 kilometre or so for various parts of the main rings. And they're almost totally made up of small, that's sort of 1 centimetre to 10 metre, particles of water ice. They're also relatively young. It's thought that they formed within the last 100 million years or so and may well disappear in about another 300 million years or less. And in fact you can see the thickness of the rings, or get an idea of the thickness of the rings, in the following picture here, which also shows the moon Titan. Here's the Titan, and you can just see the rings sort of more or less edge on here, and the shadow of the rings on the surface of the planet down there. And this picture was taken about 500,000 miles from Titan, and as mentioned in that video, the European Space Agency had a lander which piggybacked on Cassini and actually landed on Titan. And Titan is the only moon in the solar system with a thick atmosphere. In fact, it's so thick that it's difficult to see through it. You can see in this picture it really looks quite bland. And the Huygens lander parachuted down onto the surface of Titan. And, well, here's one of the pictures it took, looking downwards as it went. And really, for all the world, these things look like a river valley. Sort of river running into a lake or something. Indeed, that's what it would be if it was on the Earth. Although in this case, the sea or the lake round here is actually currently dry, and the surface temperature on Titan is about minus 180 degrees centigrade. So it ain't going to be water. But despite this, Titan does actually have liquid lakes and seas, and these can be kind of seen by bouncing radar signals off the surface, and this is what the Cassini spacecraft did. And the following video is a number of such images sort of put together to form a flyover, so you get a sort of feel for what's going on. The areas on that video which are blank had no measurements taken. And so these lakes on Titan, as I said, temperature is minus 180 degrees, are actually likely methane and ethane. So we have liquid, it's cold enough there for these liquid hydrocarbons to form, and in fact it rains. And it rains methane, ethane. Last year, 2019, NASA announced a mission to Titan called Dragonfly, and the idea of that, it will be a large helicopter, quadcopter type of thing, which is able to fly from location to location, and the plan is for that to land on Titan in 2034 if it happens. And I guess the helicopter on Mars carried by the Perseverance rover will be a good test for that sort of thing. Let's look at one of the other moons. This is Enceladus. It's actually quite small. It's only 500 kilometres across. But the observations indicate that beneath this icy covering, which you can see here, it actually has a global liquid ocean. And if that's liquid, it implies, this is water liquid, it implies there's an energy source. Something's got to be keeping it warm. And it may just be a possible place where life could develop. Okay, and recent results, when 2018, when Cassini flew through some of these water vapour jets which were emitted from these sort of stripy areas down at the bottom around here, and you saw that in the Cassini video. And there are some hints of complex organic molecules in that water vapour. And once again, Saturn is visible this week as you're viewing this. That's August. Beyond Saturn, there are the planets Uranus and then Neptune, both gas giants, sometimes dubbed the ice giants, similar but smaller than Jupiter and Saturn. And beyond these we reach the Edgeworth-Kuiper belt of smaller objects, and probably the largest of these is the dwarf planet Pluto. And we have an image of Pluto coming up. This was taken by the New Horizons mission, which a few years past actually flew past Pluto. It wasn't able to stop and examine it for any lengthy period of time, but it got some amazing images, and Pluto is actually much more interesting than was originally thought. There's a lot more going on there. So let's move on again anyway. So here's where we were, and I'm going to zoom out once more. So everything that was on that previous slide is now within this little dot here. And in fact I've exaggerated the size of the little dot because otherwise you won't be able to see it. And this is the Oort cloud. And this is admittedly a theoretical cloud, nobody's observed it, but it is thought this is where comets come from. The sort of comets that occasionally grace our skies are mainly dislodged from this Oort cloud of comet-like bodies. And again, travelling at the speed of light, we'll get to the edge of the Oort cloud in about 173 days. So it's huge. I'm going to zoom out again. Okay, so here we have the Oort cloud on the left, and on the right, that closest star, remember, Proxima Centauri, little over 4 years away at light speed. And so Proxima Centauri, 4 light years away. That's 401,410 billion kilometres. And apart from the Sun, that's the closest star to us. But there are, of course, plenty of other stars. If you look out on a clear dark night away from light pollution, you'll see probably at most a few thousand individual stars. look through a telescope though, and you get thousands and thousands more. And this picture, taken by European Southern Observatory, is a picture of a globular cluster called UKS1. Keep going. Stars range in size from about 1/10 the mass of the Sun to about 150 times the mass of the Sun, although there are some which are much, much bigger. And here is one that's about 45 times the mass. And this is actually the Bubble Nebula, and it's about a bit over 7,000 light years away in the constellation of Cassiopeia, and in itself it's about 7 light years across. This particular star generates a very strong stellar wind. Its material being pushed out from that star is moving at 4 million miles an hour, and it's pushing back the cold gas that surrounds this star, and that's what's forming this sort of bubble of material. And the gas is more dense on one side of the bubble, which is why the star is off centre. And up at the top left, in this sort of corner up here, I'm going to find my cursor, there we go. That's cool hydrogen and nitrogen gas and dust. So there's a lot more out there than just stars. There's lots of gas and really what astronomers call dust, which is more or less everything else. Okay, another good example of gas and dust is this. This is the Orion Nebula. M42 is its catalogue number. And you can see this as a faint fuzzy patch below the belt in the constellation of Orion, although you will have to wait until later in the year before that rises. And this is a massive cloud of gas and dust, and it's been illuminated by the light of new stars forming in it. And in our galaxy, about one new star forms every year in this sort of a way. Anyway, here we were. We know that stars aren't distributed evenly throughout space. Look up into the sky, especially of a summer night, and you see the Milky Way, a band of hundreds of thousands of stars going almost directly above you. Well, away from that band, the stars are relatively sparse. So let me zoom out again to give you a sort of feel for how they're arranged. All the stars that you can see, including the Sun, and all of the gas and dust, are members of what we call the Milky Way galaxy. And the Milky Way galaxy has somewhere between 100 and 400 billion stars in it, and at least 100 billion planets, by the way. And it's about 100,000 to 180,000 light years across from side to side. And we're looking face down onto it. On this, has to be said, artist's impression. And the Sun itself orbits around the centre of the galaxy, and it takes about 200 billion years to complete one orbit. So it's a bit like a Catherine wheel, and if we could look at it edge on, it would look something like this. This is actually a real galaxy, but it looks something like the Milky Way looks if we looked at it edge on. And so this dark band around here isn't actually lack of stars, it's just that the light from the stars are being absorbed by some of that dust that I mentioned earlier, and so it appears dark. And notice also that it's warped, and this is also true of the Milky Way galaxy. And if this was our galaxy, the Sun would be about here, say. And if you look in that direction, or if you look in that direction, you see a lot more stars than if you look in that direction or that direction. And so look there, and you see the Milky Way, and look there and there, you're looking away from the Milky Way. And at this time of year, again August, if you look sort of low down on the southern horizon, you're looking towards the centre of the general direction of the centre of our own galaxy. All right. So, is the Milky Way our place in space? Remember, this talk was called Our Place in Space. Well, yes, but there's more to it than that. There are other galaxies. So let's continue going outwards. And if we head out from the Sun, we'll continue passing stars for maybe about the next 50,000 years or so, depending on the exact direction we go. And then we'll leave the Milky Way galaxy. So I'm going to zoom out once more. And look, we've got another galaxy over here. This is called the Andromeda Galaxy, or M31. Here's us, here's Andromeda. And from here to here, at the speed of light, is about 2 million years. Maybe a little bit over. Okay, the Andromeda Galaxy itself, here's a bigger picture of it. You can see this with the unaided eye on a dark night. It's visible as a faint fuzzy patch of light in the constellation of Andromeda. Faint and fuzzy, but it's probably about the same size, or actually probably slightly larger than our own galaxy. And in fact, in this picture, all of these sort of small dots of stars around here are foreground stars. They're in our own galaxy, that we're simply looking past them towards Andromeda. And the Milky Way galaxy and this one, M31, are actually the largest members of a small group of 50 odd or more galaxies with a total size of about 10 million light years. Here's the way they're sort of arranged. And it's called the local galactic group. So, Milky Way, Andromeda, and various smaller galaxies, some of them a bit bigger than others. Now, you might be suspicious by the term local that has been used here, which kind of implies that there's more, and you would in fact be correct. The local group is part of the much larger VIRGO supercluster of galaxies. So I'm going to zoom out once more. Here's our little local group. And the VIRGO supercluster is about 110 million light years across. So light takes 110 million years to get from one side of this to the other. Are there more superclusters? Yes, of course there are. Here we go. Zoom out again. The size scale we're now looking at is 1 billion light years across, 1,000 million light years across. And there are whole numbers of superclusters of galaxies, and in between it's relatively empty. So there are voids, if you like. Now, once again, this has been dubbed local, and that may rouse suspicions that this isn't all, and again, it isn't. The size of the observable universe is 100 times larger than this. So we're now looking at part of the universe 100 billion light years across. The actual universe itself may be a lot bigger still, we just can't see that far. So it's kind of here, I think, that I'm going to say this is our place in space. An obvious question to follow on from this is just how many galaxies are there then? And before I answer this, I'm going to show you an image of a small area of sky. Here it is, and the small area of sky is the one marked XDF here, and we pop the moon on to give you an idea of the scale of it. So it's really quite a small bit of sky. And this is in a constellation called Fornax, the Furnace, in the southern hemisphere. And the Hubble Space Telescope took quite a deep picture in this region here, and here it is. Now, almost everything in this picture is a galaxy, apart from obvious things. Here's a foreground star. But almost everything else that I can see is a galaxy. And in fact, somebody's counted them, and there are about 5,500 of them. And so on this basis we can estimate the number of galaxies in the observable universe, and it's around 200 billion. And so while we're out here, I'm going to pay a brief visit to the furthest object yet discovered. Now actually this isn't a totally cut and dried case. There could be further known objects, but the distance isn't confirmed yet. This one, however, has been, and here it is. This is part of a field. This main picture is part of the sky in Ursa Major, the Great Bear, and it in itself contains tens of thousands of galaxies, of which one here, sort of enlarged here so you can see it, called GNZ11, is the most distant confirmed object. And it's a bright new galaxy, brimful with new hot blue stars, and they're being formed at the rate of about 20 times that in which stars are forming in the Milky Way at present. And it only appears red because it's actually receding from us at high speed, but more about that later. The distance of this object, well, it's taken the light from that almost 13.5 billion light years to make it to us. So we're seeing this galaxy as it was 13.5 billion years ago, which is about 400 million years after the Big Bang. So we're not only travelling in space by looking at these distant objects, we're travelling in time. Now actually this galaxy is now much further than 13 billion light years away from us, because it's been receding in all the time that the light has been taken to get to us. So it's currently actually around 32 billion light years away. And I said the difference is because the universe itself is expanding. But that is another story for later on. So before I finish, and really just to cement what I've talked about in your minds, here's a video, it's quite well known, by an Australian radio astronomer called Daniel Obreschkow, if I pronounced that correctly. And this sort of starts off on the Earth and then goes outwards and also inwards. So see what you think. Well, that's the end of our place in space. I hope you enjoyed it and got something out of it. The next talk is going to be about stars, and so I've called it Starlight. See you then. Bye bye.